Bismillahirrahmanirrahim. We are now recording the 15th lecture on this course of Mechanics of Materials. We have already discussed transformation of stresses in the previous two lectures, and now we are going to talk about Morse circle. Morse circle is an alternate method for finding the same solutions, so we will be solving some of the problems that we have already solved using the equations that we had developed in the transformation of stresses. But we will first learn how to draw this Morse circle. So let us see what a Morse circle is. Now we have already seen that the two equations for sigma x prime and tau x prime y prime, those are the parametric equations of a circle, and the parameter is 2 theta. So we have already seen this circle, which we can plot on the sigma versus tau scale, and this is the point where sigma is going to be maximum, this is the point where sigma is going to be minimum. However, to draw this circle, what we need is just the given data. We know the values of sigma x, sigma y and tau xy. These are going to be, in general, these values are going to be given to us. So what we need to do is just plot 2 points on the sigma versus tau scale. So these are sigma tau axes. This is sigma axis on the horizontal line, and the vertical line is the tau axis. And on this axis system, we are just going to plot 2 points, which are points x and y. Point x has the coordinates sigma x and minus tau xy. So these values are given to us, sigma x and minus tau xy. We are assuming that this tau xy is positive, so we plot actually minus tau xy. And the second point that we plot is point y. The coordinates of point y are sigma y and plus tau xy. So we just need to plot these 2 points, and then we can draw the circle. How we will draw the circle? We will just join these 2 points x and y with a straight line, and wherever this straight line intersects the horizontal axis, that point is going to be the center of the circle. If you evaluate the value of stress as at this point C, the normal stress at this point C will come out to be equal to sigma average that we have earlier discussed. So this is going to be equal to sigma x plus sigma y divided by 2. So now this point is going to be the center, so we can just, keeping this point C as the center, we can just draw this circle through points x and y. Both this distance Cx and Cy is going to be equal to r. The vertical height in both the cases is tau xy. This is minus tau xy, this is plus tau xy. So this height is tau xy, this height is tau xy. And this horizontal distance, this is going to be up to this dotted line from point C. This is going to be equal to sigma x minus sigma y divided by 2. The horizontal coordinate of this point x is sigma x, so this total distance is sigma x from O to point x. The horizontal distance is sigma x, and from O to between points O and y, the origin and y, the horizontal distance is sigma y. So this total distance between the two dotted lines that we are seeing on this figure, this is equal to sigma x minus sigma y. And since these two are similar triangles, this angle is 90 degrees, this angle is 90 degrees, this angle is same as this angle from geometry. So all the 3 angles are same, and this is equal to radius, this is equal to radius, so these 2 sides are same. So all these sides, this side is also going to be is also same as this. So this side is also, this base is also going to be equal to this base. So this is going to be half of the distance between, horizontal distance between points x and y, and the horizontal distance is sigma x minus sigma y. So this side is equal to sigma x minus sigma y divided by 2. This is equal to sigma x minus sigma y divided by 2. So this radius is going to be equal to sigma x minus sigma y divided by 2 whole square plus this tau xy under root, tau xy square under the root. This side hypotenuse is equal to this square plus this square under the root. So this square plus this square under the root, and we have already seen this formula in the previous article, using which we have solved some problems also. So this is equal to radius. Again, we can find the coordinates of sigma c also. The horizontal distance between point O and point Y is sigma y, and the horizontal distance between this foot of this dotted line and the center, this distance is sigma x minus sigma y divided by 2. So when we add these two, that is this sigma y up to this dotted line plus this distance, which is sigma x minus sigma y divided by 2, when we add these two, we will get sigma x plus sigma y divided by 2, which is sigma average, and which is also the center of the circle, as we have discussed when we developed the equation for the circle. So when we just draw this circle, then we can find, this is going to be the, we can find the radius. So this is going to be equal to the maximum in plane shear stress. So maximum in plane shear stress is going to be at the top point and at this bottom point. Then sigma c plus r is going to be equal to the maximum normal stress. This is sigma max, which is equal to sigma c plus r, and sigma c minus r is going to be equal to the minimum normal stress. This angle is going to be 2 theta p, because this line cx, it is representing the, each radial line on this circle is going to represent some plane. This radial line cx, it is representing vertical plane. The stresses on this vertical plane, the normal stress is sigma x, shear stress is tau xy. So this is the vertical plane. This line cx is representing the vertical plane. This line cy is representing the horizontal plane. On the horizontal plane, we have sigma y as the normal stress and tau xy as the shear stress. So this line cy is representing a horizontal plane. This line CA, this is representing principal plane P1. This is representing principal plane, because at point A we have maximum normal stress, and maximum and minimum normal stresses are termed as the principal stresses. So this point A, when we join this with the center, this line CA is representing the principal plane. So angle between this principal plane and the vertical plane, that is going to be equal to the twice the angle theta p, because on the equations that we have developed were in terms of 2 theta, so we are going to have 2 theta on this smooth circle. So using which we can determine the maximum normal stress, which is going to be at point A. We can determine the minimum normal stress, which is going to be point P, the maximum in plane shear stress, which is going to be the radius. So we can find Cx or Cy. We can determine the angle made by the principal plane with the vertical plane or with the horizontal plane. So we can find these angles, and the angle will start from the vertical plane. So the direction is going to be this, and if the direction is counterclockwise, we take it as positive. So this angle is going to be positive. So that is how we draw the Morse circle. Let us see if we have covered all the points. You can see this tangent of this triangle. In this triangle, tangent of this angle 2 theta p is equal to perpendicular, which is tau xy divided by base. Base is sigma x minus sigma y divided by 2. So we get to this relationship, which is same as the tangent 2 theta p that we have developed earlier in the previous article. We can also find stresses on any oblique plane which is making some angle with the, say, vertical plane or with the horizontal plane. Say we want to find stresses on a plane which is making an angle of 30 degrees with the vertical plane. Cx is representing vertical plane. Now the plane is making an angle of 30 degrees with the vertical plane, so we can draw a line which is making an angle 2 theta with this line Cx. 2 theta, when theta is equal to 30 degrees, 2 theta is going to be 60 degrees. So we can draw a line which is making an angle, say this line, which is making an angle of 60 degrees with the line Cx. And we can find the coordinates of this point where this line is intersecting the 60 degree line, where it is intersecting the circle. That the coordinates of that point are going to be the normal and shear stress at that point. So we can determine the stresses at any point on the circle, and those are going to be the normal and shear stresses on the plane which is represented by the radial line joining the center with that point. So the angle for that plane is going to be, this angle is going to be 2 theta. So that can be seen from the Morse circle. So we can find the principal stresses, we can find the maximum in plane shear stress, we can find the angles made by the principal planes, and we can also find stresses on any oblique plane. So almost everything can be found from the Morse circle. You can see the two planes here. This is sigma x and sigma y plane. So the given stresses are sigma x, tau xy, and sigma y, and these are the principal planes. This is theta p. Now this is theta p. This vertical plane is making an angle of theta p with this vertical plane, and this horizontal plane is making an angle of theta p with this horizontal plane. So this is angle theta p, which is going to be half of this. So this is your principal plane. These two are your principal planes, which are making an angle theta p with the x-axis. So that theta p is going to be half of this. So this is a sketch of the principal planes. Now you can just look at this example in which we have this is the value of sigma x 50 megapascals, sigma y is minus 10 megapascals because it is compressive, and tau xy is plus 40 megapascals. So we plot point x will have the coordinates 50 and minus 40, so it is 50 and minus 40, and point y is going to have the coordinates minus 10, which is the value of sigma y, and plus tau xy, which is plus 40. So we plot these 2 points, which are 50 minus 40 and minus 10 plus 40. This is minus 10. So we just join these 2 points wherever these two wherever this line xy intersects the horizontal axis. We can keep that point as the center and draw a circle through points x and y. So this is the Mohr circle, and in this construct Mohr circle, determine the principal stresses, determine the maximum shearing stress and the corresponding normal stress. Okay, so the maximum shearing stress is going to be at the top point, and the value of normal stress at that point is going to be equal to sigma average, because the maximum and maximum shear stress is going to be on this vertical line which will pass through the center. So the value of sigma at those planes is going to be sigma average, which is 20 megapascals. So you can see here in this shaded triangle, CF, this is going to be equal to this 50 minus this 20, which is 30. He has already calculated sigma average, which is sigma x plus sigma y divided by 2. So the coordinate of the center is 20, and in this triangle we have CF is equal to 50 minus 20, and Fx is equal to tau xy, which is 40. So we can find R. It is 30 square plus 40 square under root, which comes out to be 50 megapascals. So this R is going to be equal to the maximum in plane shear stress. Okay, now we will look at some problems. The 2 problems that we have already solved using the equations. This is problem 7.31, and we have to solve problem 7.5 that we have already solved using the equations that we had developed. Now the value of sigma x is minus 60 megapascals, sigma y is minus 40 megapascals, tau xy is 35 megapascals. So point x is going to be sigma x minus tau xy. Sigma x is minus 60, tau xy is 35. So coordinates of point x are going to be minus 60 and minus 35. And coordinates of point y, those are going to be sigma y and tau xy. Sigma y is minus 40 and tau xy is 35. So minus 40 plus 35 are going to be the coordinates of point y. So we have this point y and this point x. So we will just plot these 2 points on the sigma versus tau plane, and we join these 2 points, and wherever this line xy intersects the horizontal axis, that is going to be the center of the circle, and then we can just draw a circle through points x and y. Now in problem 7.5 we were to find the principal planes and the principal stresses. So the principal plane, one principal plane is going to be this, the other principal plane is going to be this. So we can find the angles made by, this is the vertical plane, Cx is the vertical plane, this one, where the stress is minus 60, this one. So this distance in this triangle that we can see here, this height is going to be equal to the shear stress, the vertical coordinate of this point x. So this is 35, and this is going to be equal to 10, because the average normal stress is going to be equal to minus 60 minus 40 divided by 2, which comes out to be minus 40, sigma x plus sigma y divided by 2. So the coordinates of point C are going to be minus 50, 0. This angle theta, which is made by the vertical plane with this plane P2, that is going to be equal to twice theta. P is this angle is going to be tan inverse perpendicular work base. This comes out to be 74 degrees. So this 2 theta P, it is 180 minus this angle theta, so this comes out to be 53 degrees. So and this theta P2 is going to be equal to, this angle is going to be negative, because we start from this vertical plane, and this rotation is going to be counterclockwise, which we are taking as positive. So this angle will be positive, which is 53, and this angle clockwise will be negative, so this is going to be minus 37. Now the values of principal stresses, we can find the this radius Cx, r is equal to 35 square plus 10 square under root, so it is 36.4, and sigma P1 is going to be sigma C plus r, so it is minus 13.6 megapascals, and sigma P2 is going to be sigma C minus r, so it is minus 86.4 megapascals. So these are the same results that we had obtained in the solution of problem 7.5. So just see the drawing of circle again. We just find the coordinates of this point x and this point y, and draw these points on the sigma versus tau plane, sigma on the horizontal axis, tau on the vertical axis, and then we can join these 2 points with a straight line, and wherever this straight line intersects the horizontal axis, that gives us the center of the circle, and we can, keeping that as the center, we can draw a circle through points x and y, and then we can find the angles made by the principal planes with respect to the vertical or with respect to the horizontal planes. So rest is going to be simple geometry. Okay, now we look at the second problem. We have also solved this problem. This problem 750. We have solved this problem also, in which we were to find the largest value of sigma y. Largest value of sigma y, for which the maximum in plane shear stress is equal to 75 megapascals. So we are given the maximum in plane shearing stress, which is the radius of the Morse circle. So radius is given to us. So we know sigma x, we know the value of tau xy, so we can plot point x, which is having coordinates sigma x minus tau xy. So 60 and minus 20. 60 minus 20 is this point. We plot this point here with respect to the origin. Now we have to draw a line. We have to draw a line for which the radius is going to be equal to 75. So for that we can just look at this triangle. We can this distance, this height is going to be 20 for point x. This height is going to be 20, and this radius is going to be 75. So we can determine this distance. This comes out to be 75 square minus 20 square under root, which comes out to be 72.3. So this distance is 72.3. So we can locate the center. We can locate the center. Center is going to be this 60 plus 72.3. This is the value of stress at the center. In this we were not given sigma y, so we could not draw the circle like that. So we have to. Now there are two possibilities in this problem. As you can see that there are two circles which are plotted. One is the solid circle, the other one is shown with dotted line. There can be two possibilities. Sigma y can be smaller than sigma x, and sigma y can also be larger than sigma x. Since we have to find the largest value of sigma y for which the maximum shear stress is not going to exceed 75 megapascals, so since we have to find the larger value, so we will consider this circle for which sigma y is going to be larger. In this case, for this dotted circle, sigma y is going to be smaller. So we have to find the larger value, so we will consider this circle. We can draw the circle on the right of point x, we can draw the circle on the left of point x. The circle on the left of point x will have sigma y less than sigma x, and the circle on the right of sigma x will have sigma y greater than sigma x. Since we have to find the greater value, so we consider the circle which is on the right of this point x. So we can look at this triangle. This distance is 72.3, and similarly this distance, horizontal distance between point C and point Y, is also going to be 72.3. So sigma C comes out to be the value of normal stress at this point x is 60. So horizontal distance between point O, origin, and x is 60. So 60 plus this distance, which is 72.3, that comes out to be 132.3. This gives us the value of sigma C, the value of normal stress at the center of the circle. And then to find sigma y is again going to be this sigma C plus 72.3. So that gives us 204.6 megapascals. So this is the largest value for which the shear stress is not going to exceed 75 megapascals. If we reduce this value, say it is 200, then this point will come down, and you will see that the radius is going to be smaller. This point will move towards left. This point will move towards left when sigma y is smaller. So in that case the radius is going to be smaller. So that means maximum shear stress is going to be smaller. So this will give us the largest value of sigma y, for which the shear stress is not going to exceed 75 megapascals. So the solution, you can see how simple it becomes when we use the Morse circle. We can find anything from the Morse circle. So I hope this is understood by all the students. So we will have an online session on this on Monday. So if you have any questions, we can discuss in that. So in the next lecture, which is most likely going to be the last lecture for the course, we will probably solve another problem and look at the maximum shear stress from the three-dimensional perspective. So that will conclude the course. Okay, we will stop here and we will have online session on this. Thank you.